My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself. So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving. So this is the 3-dimensional positions of lines, edges, curbs, traffic signs, traffic lights, cars, their positions, orientations, depths, velocities, and so on. So here I'm showing a video of, actually, hold on. Apologies. So here I'm showing the video of the raw inputs that come into the stack, and then the neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car. Now, what I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So we are building, of course, all of the mechanical components of the body, the nervous system, which is all of the electrical components, and for our purposes, the brain of the Autopilot, and specifically for this section, the synthetic visual cortex. Now, the biological visual cortex actually has quite intricate structure and a number of areas that organize the information flow of this brain. And so in particular, in your visual cortices, the information hits the light, hits the retina, goes through the LGN all the way to the back of your visual cortex, goes through areas V1, V2, V4, the IT, the ventral and the dorsal streams, and the information is organized in a certain layout. And so when we are designing the visual cortex of the car, we also want to design the neural network architecture of how the information flows in the system. So the processing starts in the beginning when light hits our artificial retina, and we are going to process this information with neural networks. Now, I'm going to roughly organize this section chronologically. So starting off with some of the neural networks and what they looked like roughly 4 years ago when I joined the team, and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane going forward on the highway. And so it had to keep lane and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So this processing took the following shape. We take a 1280 by 960 input, and this is 12-bit integers streaming in at roughly 36 hertz. Now we're going to process that with a neural network. So we instantiate a feature extractor backbone. In this case, we use residual neural networks. So we have a stem and a number of residual blocks connected in series. Now the specific class of ResNets that we use are RegNets, because RegNets offer a very nice design space for neural networks because they allow you to very nicely trade off latency and accuracy. Now these RegNets give us as an output a number of features at different resolutions and different scales. So in particular, on the very bottom of this feature hierarchy, we have very high resolution information with very low channel counts. And all the way at the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and a lot of that context, have a lot of that scene context. We then like to process this with feature pyramid networks. In our case, we like to use BiFBNs. And they get to multiple scales to talk to each other effectively and share a lot of information. So for example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. After a BiFBN and a feature fusion across scales, we then go into task-specific heads. So for example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly we converged in this kind of a architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, HydraNets, and these are the heads of the Hydra. Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on, and you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive. And number three, because there's this bottleneck here in features, what we do fairly often is that we actually cache these features to disk, and when we are doing these fine-tuning workflows, we only fine-tune from the cached features up and only fine-tune the heads. So most often in terms of our training workflows, we will do an end-to-end training run once in a while where we train everything jointly, then we cache the features at the multi-scale feature level, and then we fine-tune off of that for a while, and then end-to-end train once again, and so on. So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these HydraNets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked, all of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the HydraNet. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we call the Occupancy Tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now there were two major problems, I would say, with this setup. Number one, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end to end. Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible. And we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space. And the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in these in every single pixel of the image. And also if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly, the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, So there are two problems with this. Problem number one, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number two, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling in images and so on is not going to get you there. You need vector space labels. We're going to talk a lot more about problem number two later in the talk. For now, I want to focus on the neural network architectures, so I'm going to deep dive into problem number one. So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images. And the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data-dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space. And this transformer it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values, and then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff, and that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation. So if you do all of the engineering correctly, this again is very easily said, difficult to do. You do all of the engineering correctly. There's one more problem actually before. I'm not sure what's up with the slides. So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. And so you could definitely just like concatenate the camera calibrations of all of the images and somehow feed them in with an MLP. But actually, we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. So this is what that would look like. We insert a new layer right above the image, rectification layer. It's a function of camera calibration, and it translates all of the images into a virtual common camera. So if you were to average up a lot of repeater images, for example, which face to the back, without doing this, you would get a kind of a blur. But after doing the rectification transformation, you see that the back mirror gets really crisp. So once you do this, this improves the performance quite a bit. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. Okay, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space, but we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context, and we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's the feature queue and the rough layout of it. We are basically concatenating these features over time and the kinematics of how the car has moved and the positional encodings, and that's being concatenated, encoded, and stored in a feature queue. And that's going to be consumed by a video module. Now, there's a few details here, again, to get right. So in particular, with respect to the pop and push mechanisms, and when do you push, and how, and especially when do you push, basically. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter the features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Now, for the video module, we looked at a number of possibilities of how to fuse this information temporally. So we looked at three-dimensional convolutions, transformers, axial transformers in an effort to try to make them more efficient, recurrent neural networks of a large number of flavors. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of. So here's an example of what that looks like. Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN, and these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road, like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the Spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent. And you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the Spatial RNN, and then continues into the branching structure of the HydraNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements, so this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road, maybe like point by point, or in some other fashion that doesn't require expensive post-processing. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run plane and control on top of it.